Okay. Okay. So this is so today's date is the 31st of January 2026. The time now is midnight. The midnight at 1:10 a.m. 10 minutes past midnight. So continue the video here. Well, this is basically because I'm not tired. So we're gonna have video here. Yeah. So this video is basically on the Trident verifier. But you don't need to verify this. It's not going to verify. You're going to work on the um, the compass system for the system. Because the must go somewhere before we do the verifier. So we're going to get the compass system, try the compass system for the XYZ coordinate system via geo coordinate system. So you can send a message to system, you send it to its programming system. So you can send it to three people um, three people or LAN network. So let me get started on the board. On the board, let's get started here. So I got the white choke. I got the white choke. I wasn't seeing the board fully. So the close the board now. I got the white choke. I got the green choke. I don't have the blue choke, so I put it away. No blue choke today. So I put it here. So you get yeah. So let's start with the topology first, or the topography first before we start with the actual system. So we got standard peer-to-peer topology. We got P2P, P2P, we got two types of this P2P. We get a circle and we get X. So the circle needs is a node. It needs dynamic. So the circle is dynamic. The X is static. Think of them as a addressing system, IP addressing. This is basically the problem of IP addressing problems in the space of. But these are just mobs of systems. For me, I use it as a line system for local RNA for local pen topology. So, for example, your friend can be here. Your friend can be here and send the message to you on the peer-to-peer topology. Notice that the circle is a dynamic system, dynamic, the circle, a dynamic IP that can switch to the chain context. A dynamic can change context, and you get a static IP, which is X. X. So O is that O node is dynamic, cross is a static IP. Static IP. So let's first this is the model here. So let's get to the second page before we discuss the next step. The next step is the next model. So this model is peer to peer. We also got first which here bus. So this peer to peer here bus, which is basically interdependency. So you get a bus, which is like the bus wheels. You get bus wheels. Um, and you get so you, as you can see here, the circles are static IPs, but this cross where they cross here is static, and this basically maps over the place. So this is possible with the topology X axis. So when you see the bus topology has like wheels, you get like an area here, a curved area here. You get where the via the range of the system. But you also get another configuration, which is a triangular model. So the end content connects here. So so let me give you the camera closer. So you get here a model here for the system. Yeah. And you get one more, which is a hybrid model. So this is sometimes, so as you can see, here's a peer-to-peer topology, static IP, and static with a circle and square. So you get two static IPs in one dynamic IP, so you can use two static IPs to one dynamic. So you have two IPs can be referred to like a virtual IP, which would be this is a dynamic system in the making. So you can get a virtual IP, and that's how that works. You get two static IPs, and then you get this kind of model. These are the bus rules on the ground, which they basically map out the ground of a plan, you like a floor plan. So you look on floor plans. This you can use for a wide area network, a wide no not wide it's wild and the word wide like it's sparse. It's basically modeled on the some rough of the system, but the area covered is this kind of triangle here or this triangle here. But this is basically the physical wires system has to be here. Yeah. So if you go to connection here, here, and here, and here. And equation will represent systems of these equations will be solving the system. So this would be a computer program on a computer here. If it's a centralized computer, and this startup will be a centralized computer. So this is a bus topology. Now we get a hybrid model here. So the hybrid model will be this. And this will be this. As you can see, this is a star. This is two triangles overlapping. Two triangles, two equality triangles overlapping. Close to scale. So two, the edges are either tank or stack. This one, if I have a stack IP at the edges of the triangles, they have an area to cover. That area is always going to be signal. You have a signal there. You have some kind of signal there. And this IP address is called a hybrid function. But it's a work on the total area. So the areas are here. One, two, three, four, five. The areas are you have six areas of coverage, and these areas are being controlled. So-called coverage areas. You can always get local OS. So this is more called tomography. Tomography, not topology. You get topology, which is the area, perimeter of the area. Then you get the actual area, which is the tomography measurement of distance. You get tomography. So we have one, two, three, four, five, six areas of smaller triangles you can cover on one, two, three, four, five, six, seven. One, two, three, four, five, six, seven. Seven areas of smaller triangles you can cover if you have two overlapping triangles. And when they talk about they have coverage, you have something with total. So the number seven is the area of tomography area, which is or service area. You can offer services to people via this mobility schema. But we just fill over this schema. So if you don't know this, you only put it here. So put it here. Nothing to do. So service operation, the open system. Operation service. So you get service operation of OB Nexus. Let me do the alpha now. So that, let's call the go. So the, so the services are here already. So one next. So how does this work? Mathematically, this works by the verified works informally by creating a yes no maybe trident, which means what is this message? What do I decide? What do you do with this? Yes no maybe. Yes, no, or maybe trident. So the trident is Cisco or Risco. Now Cisco is bottom-up execution order, and Risco is risk instruction set, which is like a risk instruction set, which is like a Cisco or Risco, which is basically which is top-down resolution for assembly languages. Because assembly is executable if you want it to be executable. Um, Assembly is executable if you want to. I think so. So you get the shape of you get this okay here. So you get yes, no, maybe as triangles here. You see, so this is compass. The compass. So in the compass you have a filter flash sequence, and the filter flash sequence works like this. So you remember the older chaos model we had in last video? They have four. four states to resolve to, four four resultant states: order or chaos, order and chaos. So you have filter and flash. So you have filter. Let me define it properly. So a filter is a source. A filter is a function. Filter is any algorithm that sorts data but does not mutate the data. Mutate the data. So you can have the sort or mute sort and never mutate. Never mutates. Results. So the result is a sort organized. What the operation does, and the flash does the opposite. The flash mutates the results. Mutate. Well, think of filter results. That's the filter. So it's a filter flash bidirectional sequences. And you get these filter flash sequences are happening in your computer once the processing. So they will put the processing order in this one, in the Cisco and this one. Now get a Cisco, CISCO, which is bottom up bottom up execution order, which is like an execution order, which is basically NASAM, network assembler. NASAM uses this, and you get RISCO, which is the old instruction set, which is like the older one, which is like top down execution. But this is when you get to run. So this execution, this is what assembly uses. Um, the both instruction set, which we call the assembly instruction set. So now you get the order and chaos model, the bipartite system. Bipartite. So the bipartite system is basically a promise or feature of Python, a feature library. So get a bipartite order and system resolve order. This is it's a promise that doesn't want to pen. It doesn't like pending. It doesn't like pending. It's a promise that's resolved because so if you get a promise library, a feature library in Python, you come up with features, but they have a pending state. They have a yield state. So yield state is dynamic. So this is what resolve itself. This is the seeking. So yield state basically has the system has some default iota that resolve the state. So the iota are classifiers. So you get to bypassed ordering, which is by order. If you get order, you have chaos, and the chaos are a result of a system's trident, which can be example here. So you have triangle. So triangle is basically a triangle. A triangle here. So triangle here, and this is put in quadrants here. So you have this compass here. This is a compass here, but you can't see it's even out. It's new compass. So you have new compass. Compass has a direction. So this is a point, the pin of a compass, and the pin of a compass represents kind of the model we're using for the bypass order. So to mitigate order, let's be case amongst the bypass systems. So if this compass is rotated, spinning this needle, this is the needle of the compass, where is this order and chaos happening? So you have four tomography states of the system, and that's basically based on the system of natural world entropy around the world. Get information from nothing. How things can mean something that we don't really know it means something based on frame of reference. So the system. Example, we have no signal. We have the nuclear bit sequence, which is like a noise means the system is can be destroyed by entropy. It's basically we have no information we're getting. We're just getting noise, random data, things we can't read. Too much information, too little data, too little. And then noise. You get noise. Okay, then you get noise, no noise. So the system is reaching an equilibrium. There's no noise in the environment. There's no noise in the environment. You need a clear picture. So noise is no noise, but this noise has to be ordered by bypassers ordering all chaos. You get noise, no noise. You get no noise, then you get no signal. So this is the triangle here. So you get no signal, And if you can keep control all of this system, no signal, that means you can have signal, which is the entry, which is like a so this signal you're not getting to a channel, you're not connected to someone's channel. No channel. So the channels here is noise, no noise and no signal. And the bipartisan ordering has to organize this into categories so we can always have a clear picture. And that picture is a signal, which is like a computer graphics interface signal. So this ensures no lockout, no lockout. So signal. Signal means like you are using computer as stable as it is. A signal. And signal means like you are using computer. So if no noise, you get no you get lockout. So you get signal, you get lockout, you get no lockout. So this is the lockout problem, really. VR bypass ordering. So the screen when the screen comes into place is am I having a clear picture of the message? The spring physics basically works on the kind of system of low signal transmission. You have noise here, and you have noise on the root on the top at the tip of the needle, and you have on the right root you have no noise, and you have no signal on the right root. No, and you try to make signal. But so you can think of this um, system as either filters the bio as filters. So you get one filter which is order, and the other thing is chaos. The filters are literally just like to see less and see more. To see more basically. The filters are just the things you apply to the needle to to get the RCD. So the filters are basically so you have two filters. You have one order filter, and you have one chaos filter. And the filters basically are bipartite. So you can switch them around to have to see where the pointer, where the compass needle points to. So the goal of this is to have a system that has no lockout and the system that has no lockout. That has no lockout. But lockout means the system locked you out. So it's no lockout here. There is no defined space in your own system. The system. So they never lock you out. So without lock flag system. Which is very close to the information field that works stable for everyone. So it's basically a system of that results. So mathematically, how would this work? Mathematically, this would be the same as having a yes, no, or maybe consensus, but we are the sources of bypassing order. So yes, no, maybe can use the same if you don't understand this. But the real world is noisy. So we have this yes, no, and maybe because this is basically the to replace this to anything other than one. Is yes, no, maybe just consensus. So this is the real world consensus of fact. Via the compass. So the compass does this job properly. So let me get closer to it. Let me show you what it's doing. So we talked about the bipartisan order. We'll talk about the chaos order and how there are filters, two filters. For two bypass, one bypass filter. So yeah, you can switch it with one bypass filter, one tripod, one bypass filter. You have noise, no noise, signal, signal. And this is the compass, searching space for the needle, which can dictate the result of the message and via the tomography of the state of the hybrid architecture. And this you're working on me. So the goal of this is to resolve the system perfectly. So we're not going to get to the maths now, math side of it things. But just take the visual down a filter. So you get a filter which is again it doesn't change the resultant. It just reaches the state of the state or data of the program. It doesn't change one thing. It remains the state, it keeps the same, it keeps the same, it keeps the resultant, the data. So, and the state of the program is just the filter. And you get the fault, it misses one or the other. It's a pure function that does one or the other, but it doesn't mean the result of it either of that system. You get flash, a story like it stores one thing and not the other. It preserves the state and not the data. I'm saying, and get which is basically the quantum system filter flash architecture for quantum modeling, via quantum filter tunneling. So you get a Cisco RISCO bottom up execution order, RISCO reduced instruction set, top down execution order, and you get bypass order. So I'm gonna put this here. So one now. So now I'm gonna erase this now just to continue the work of doing. So I can see so we're not supposed to bypass the order here and it's more graphic model. So, if you want, so the last thing I want to show you today is how it works mathematically, and that will be via the local sequence, no local sequence. So how this works mathematically? So normally, because it works like this, it works like yes, no, maybe system or trial system. Just determine how to verify. So the verification really works on first phases. So spring phases. So you get a source of knowledge. Remember, you get net force equals one over net force of one over x equals minus x. Net force of x equals k. Um, the integral of 0 to x is defined as the secant over time. So, think about paper, don't have a paper. So I don't have a paper now. Let me just grab what I remember. One time we get to the half, one to the two, one to the two. So 1 over e, when e is exponent, 1 over e to the power of n over 2, over 3, over 4. Oh. So you get one total, so you get the two equations you have. So you get the next force equals to 1 over x equals negative k. Now, negative k, because I'm just remember to remember with you guys. Negative k means negative kinematics, negative force, force in the opposite direction. And that force we do is the kinetic force. So you get 1 over x, and 1 over x is the force in the opposite direction. So this force has a relationship to this force k, which is the force in one other direction. And this works on xyz axis. So you get a one half of the force. One half of the force, which would be one half times d, one half times d, u, where u is the unit and d is the derivative of u. So one half of du, where is the unit? So the unit is one for the ratio to be 7, but we need the ratio. So one half of the ratio is one half of the ratio is half force which is sent. Awesome. But you get one half. But you get this is one half is one half of a pull force, of a push and a pull force. So, via work done. So the work done equation is what we need. Work equals displacement times force, and force equals mass times acceleration. So, because I can't find the document, my working out before, basically, it's individuals, I can't put my last thing. If I can, I'll pause it and check it out. Let me try it actually. Let me try and pause my live stream. Yeah, I'm not even streaming live. Okay, I thought it was. So, you see what I'm saying? So, so let me try to find my video on the system of here. So orbit no, we play chess. So we get force we get integral of fu given d cosine u over sine u given the force u. So the integral of the force u is the potential equation and this would be the potential equation. So you get 1 over E. So so I get it now. So I know I'm working on now. So let me just finish this now. Uh, so you get so you get thank you Monday. Thank you. So you get the potential equation of the integral is 1 over. So you get this work equals to displaced on D times space on displacement times force. And this force is the essential, but now you get this equation itself. So you get the other equations too, and they are um, the potential P, the potential P, the potential PE, potential of E, or the potential of so the work so the potential of a displacement D. So you get two types of work. So you get work of potential work, and you get work done. So you get this work done. Work equals displacement as force. But if you get potential work, you get a ratio to displacement. So you get the work displaced. But the work is basically work equals if you divide by F, you get displace. So you divide by F. So force divided by S. So you get also so to get displacement itself, you have to do work divided by F, and that equals to G, which equals to displacement of the system. So this displacement is what you need. But you get two types of displacement. You get potential displacement. You get two types of potential. You get potential displacement and relative displacement. So you get absolute displacement. You get potential displacement. You get absolute displacement and potential and the relative displacement. But the model is basically for modeling potential potential work or like if you're in a helicopter, you jump in off the helicopter, and you get potential work, and you get potential energy. Like if you're in a helicopter, you don't have to jump, but you don't need to jump, you just have to fall down to get the parachute. You get potential energy and um, uh, non-potential energy. So you get energy that just occurs in the system. Of course, you have to add energy somewhere. Like if you're already in gravity, you have to keep the orbit around the gravity. If you can't maintain the orbit, then you have to add more work to maintain that orbit. So work was force and displacement. So this function, this kind of formula here work divided by force equals displacement. A displacement that has two types of potential and kinematic potential and non-potential work displacement. To determine the potential work done, because they're related to work and given the force related to work, which is work divided by force equals displacement, or displacement equals work divided by force. So we get this formula here already. Now this one we have the potential, uh, the potential. So you get the potential, you get the non-potential work, non-potential. You get the displacement that's the displacement end. But I'm gonna write this down. I'm gonna write what I have here. So you get potential. We're gonna have. So not that we're gonna have the integral. So you get because my video is running low. So you get the integral x or 0 f u f comma u uh du d sorry dc sorry guys. So we do integral of x 0 f u d c s c sine u. So we get the integration, not the Laplace integration, of a force of a unit, and the unit is basically the unit of work from force or and displacement only. You need that to which is half the system. So you get half of so you get the force unit of displacement. So you get force which is of a unit displacement, the derivative of cosecant over the sine of uh, of of the unit, which is the unit measurement of the XY axis via SOHCAHTOA. So you get a system there. You get a system here. You get a force equals system here. So you get a system here. So the potential equation of the system is isomorphic system. But, this equation determines how the integration of a potential system scales via Laplace rule. So this is a very important formula to have in your mind, guys. So you now get the potential equation, which is one over e. So you get the potential equation, you get one over e. So one over e represents e times some. This is means. So this is the force. F is the force of the unit u, where u is a force being acted some kind of object being acted upon. And you get a cosine of a sine, cosecant of the unit over sine of the unit, which is just cosecant divided by secant u, where they share the same unit as input via lambda reduction. Basically, the lambda reduction wasn't the units. This is basically what's on alpha beta reduction. This is basically the same resolution one to one. And you then finally get finally get the system of the resources itself non-linearly because f times sorry guys, because one over e times kx to the power of e, one over times d, one over e, what's that e, what did I put e, kx to the power of e. So for this result itself, you have e to the power e times k of x. Uh, yeah, so you get one over. I wrote it down improperly, I think. Yeah, so you now have the e one over k e times k of x. So you get one over e. So you get one over k one over k times e to the power one over k. 1 over x, um, 1 over x, where x is the input of the share, the share 10% ratio between e and x. So that'll be 1 over e. I put e here, but should be an x. Kx times kx. Oh, I put 1 over e. So 1 over e is the exponent of the system. But the more force you have in the system, 10%, the more 1 over e, 1 divided by e, so 1 divided by e will be the threshold of the force to the maximum growth of e. So e will be an exponent. So 1 over e is correct, I believe, in my board's view, because I'm proud of it. 1 over e. So let me just put this 1 over e here. Gotta stop now. 1 divided by 1 divided by 1 divided by e, 0.3 678, 1 to 0.3679, and 1 divided by 3 times k, and k is the kinematic of the system. So you get theta over k, you get 1 over x, which is minus k, and you get x, which is just the input system. But this 1 over e determines the kind of scale of the system via the growth factor E. Now, E is usually 1 over E, so it's 10% stable, but it's the inverse ratio, so you get 1 divided by E. But this 1 divided by T is equal to 1 over 2 points, or something that's growing. So, growing in size. So 1 over E represents the inverse of the system that you're pulling back. You're holding the potential. This potential is where you can hold. Potential is between where you can send, where you can push and pull. We are putting this up to 0.3678, and then 1 over e times k. K is the counter. So if k is if the force acting on x is 45 degrees. 45, the force, the force is, the force of x, the force of x, the force given x is, displaced by, the unit d, which is k. D is k. Uh, uh, let's say, point 0.5, 45, over 100, 0.45, 0.45. And now times 0.45, 0.45. So you get one of e times k od 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 um, multiplied by x times k od, uh, 0.3679 times, 45 degrees. So that will be times 45 will be, um, 45 watts, 0.45. So times 0.45 times 0.45 is 0.166 16655 166 0.16655 55. And this unit is basically, the kind of, space. You get the force. So you get, force. So what is divided by the force? Which is what so the total work would be the force. And we know the force is what divided by force. Yeah. But one of the E is the ratio that's stable between push and pull. So if I just want to do, I just have to compute the inverse work, which is the work. So now I have one over E on the force. I have the ratio um, of 0.1666, 0.166, 0.16554, 554, 0.16554. And that was what I sent, with the system of the messages of, but so the verified will have this potential energy, and then I'll have half of that. So half of that energy will be, so let's say this is 10% stable, 10% stable. But if I have, half of this message, half of them, this would be, I have them here. Should be, so basically, 10% should be 4.5. So this is basically 1% stable message. It's not really good. So it should be, so if we're using 45, I should be using, 45. I should be using 10% of 45, which would be 4.5. So that would be 4.5 times, the kinematics times 4.5. So that'll be 45, 4.5 times the times x divided by x, which is, 4.5, should be, 4.5, divided by x would be 0.45, and, I mean, 4.5 is 10% of 45. So that'll be 4.5 times x. X would be, whatever, the ratio was of x. So, so, how you, times half of the system, because half is pull. I made a mistake, but I learned from my mistake. So, so I'm gonna round it up on a good note, but we do by calculator here, because I haven't got my calculator with me. So I get half 1 divided by 2 times x, and x is, 0.5. So x is 0.5. So 1 over each. So half of the W2 will be, minus k. So we get, times, 45 divided by 100 times 45 divided by, 10 for 10% stability, which will give you 4.5. 0.5 times, 4.5 will give you 2.25. So the message is 2.25 stable, so 2.25 is what you get. But this message is basically, what you're saying to verify neutral ruling. So for this to work properly, you're gonna have 2.25 already there, for 10%. No 5 divided by 10 is 4.5. So that works. So you're gonna have 2.25, and the 2.25 will have something else. added to it, and that last one will be the 1 over e, which would be divided by which would be the cosecant of the cosecant over the sine of u, which is 45. Because you do 10%, so we times the cosecant. Yes, cosecant will be 25.4713 divided by the sine, which would be 0.8416. Uh, and the unit is basically 45 degrees. So we get 45, 4.5 divided by 45, divided by of the units of times the unit of 45. So times the unit of 45 will be yeah. So basically, you know what I'm saying. So you get the ratio. So you get divided by the unit. No, divide. So you get to have divided by the unit of. Yeah, so basically, because last one is so given to so again, it was 4 to 5 divided by 10% stable. 45 divided by 10, 4.5 times times 1 over e times so 45 divided by 10, 45 divided by 10 times the which is the displacement of the system. 45 and then we get times so we get the force. The force equals the work. So we get the force. The force is basically the work. So the work divided by force. The work is basically the integration of the work is basically the potential. So times the integral of cosecant of u, but u is not defined. The force of u. The force is basically times the cosecant of the force, which is okay, times the cosecant, which is 12.745, which is cosecant, which is the integration over the cosecant over the area cosecant divided by sine divided by the sine of u, sine of sine of u, which is 4.5. So it's 4.5 divided by the sine of u, which is 4.5, which is 0.0 divided by the sine of u. Oh, let me just go back again. Control Z. So which is 4.5, which is 68 point 68 point one 68.15 117511 141. If you can stop in 3 2 1, okay. Guys, so basically you see the integration has worked. So I'm gonna go on the video, but you just have to take this integration formula as for notice. Listen. So you have the force cube, the force of the unit cube, which is basically due to the whole system, which is like 45 degrees or 45, you get for so it'll be force of 45 over the unit, so there'll be so basically sub the unit, so basically 45, you get 4.5, but over the ratio of 45. So this is 10% stability factor. Thank you guys for watching my video.